All right, we're going to try and figure out this angular motion problem from Unit 17 in positive physics. So we have a 1.2 kilogram bike wheel. Oh, let me undo that. All right, so we need to kind of keep track of some things here. So the mass equals 1.2 kilograms. 1.2 kilograms. And it's spinning at 210 RPMs clockwise. So omega equals 210 revolutions per minute. Now we need to convert that to radians per second. So this is what omega has to be in. So right now we have 210 revolutions per minute. So we're gonna tend to that right away. So 210 revolutions per minute. 1 revolution per minute is equal to 2 pi radians divided by 60 seconds. So now we have it in radians per second, right? So that's what omega needs to be measured in. So we're going to do a little conversion here. Anytime you have RPM, revolution per minute, that's equal to 2 pi over 60. And if I throw that in a calculator quick, 2 pi divided by 60, that's equal to 0.1047. 0.1047 KCLD if you're from St. Cloud, Minnesota. Okay, so this is our conversion factor. So RPM times 0.1047 will equal radians per second. So RPM times 0.1047 equals omega in radians per second. All right, so 0.1047 times 210, because remember we had 210 of those revolutions per minute. So 0.1047 times 210 is equal to 21.99. So we're just going to call omega 22. 22 radians per second. Okay, so that was the original speed, omega initial. And then when a student applies a frictional force is shown right here, opposing this, because this thing is turning clockwise, and this friction is pushing it counterclockwise. What is the initial angular speed? Well, right here, we're going to put in 22. 22, let's put that in there. 22, and this unit is going to be radians per second. And how much torque does the friction cause is force, torque, remember torque. So this is question B, I guess. So this is A. Torque equals force times lever arm distance, and the force is 2.25 newtons. 2.25. Oh, wait. Let me back that up. There we go. 2.25. And the lever arm distance is the distance between here and the point of rotation. So each of these squares is 10 centimeters. So it's 10, 20, 30, 40, 50 centimeters times 50 centimeters. And so that equals 2.25 Newton times 50. Let me put that in the calculator. 2.25 times 50 is 112.5. And that's equal to 112.5 Newton centimeters. Okay, so that's going to be here. And this is Newton centimeters. Not newtons per centimeter, Newton centimeters. So what is the moment of inertia? Well, moment of inertia, it says right here for the disk, is I equals mr squared. Well, m is this, and we said r was equal to 50 centimeters. So I equals mr squared. So part C, I equals mr squared. Now this is the question: do we need r to be in meters, or can r be in centimeters? So let's just figure it out here for both. So m is 1.2 kilograms. 1.2 kilograms. Let's see here. I'll put that in there. 1.2 kilograms times r squared is 50 centimeters. 50 centimeters squared, or if it's 0.5 meters squared. So 0.5 times 0.5 equals 0.25 meters squared. And 50 squared is 2,500 centimeters squared. So either way times 1.2. 1.2 times 0.25 is 0.3. So over here, if it's in meters, it's 0.3 kilogram meters squared. Kilogram meters squared. So let me back that up. I equals either 0.3 or 1.2 times 25. 1.2 times 2,500. That's equal to 3,000. Or it's equal to 3,000 kilogram centimeters squared. Kilogram centimeter squared. Okay, so that's that. And then the angular acceleration, we have to make a correlation between torque in this part B and I here. So D, the angular acceleration, torque equals I alpha, and we know torque and we know I, so we take torque divided by I and we get alpha. Hey, I'm in the middle of recording a video, and now my kids are going to hear me answering the phone right now. I was trying to send that message, but I'm going to finish this one and I'll call you right back. Love you, bye. So torque over I, that was my wife calling, she's on her way home, C equals alpha. So we'd have torque here and we'd have I here. So whatever your torque time divided by I would give you alpha for that part. And then how long will the wheel take to stop spinning? So alpha acceleration equals omega final minus omega initial over t. And we're trying to find out how much time, how long will it take. So that means we rearrange this equation and say t is equal to omega final minus omega initial over alpha. Well, we know omega final is 0, and omega initial is part A right here, 22. So alpha we found up here, and t is all we got to solve for. So omega initial over alpha. Alpha is negative, and this is negative, so that becomes a positive time. So that'll give us the time it takes. And then how far will the wheel rotate before stopping? So distance, or theta, equals, we could do this a couple different ways. Velocity, average velocity over velocity is distance over time. Velocity, average velocity times time. So the average velocity is found by v final plus v initial over 2. So it would be 11 radians per second times the time that you got from this section. Average velocity times time would give you the theta. Or if you had to work it all the way, these should work, both of these should work, is 1/2 alpha t plus omega initial t, alpha t squared plus omega initial t. Remembering that alpha is negative. So this is a negative value, and this is a positive value, 22 times the time that you got back here. And that would set you up for theta. So one of those two. So that goes through how far in radians and then in revolutions. So if you have radians, whatever number of radians you get, radians divided by 2 pi will give you revolutions. So this is how you get that one. So once you solve for radians and this one down here, or this one here, so theta is v average times t, so right here. Or if you use this equation, when you get that number, that's in radians, then take that number divided by 2 pi, that'll give you revolutions.